Hello, and today we're going to be talking about Kirchhoff's current law, or KCL for short. And pretty much what KCL says is that the current or the net current flowing into a junction, so we can say I, which is a symbol for current. So the current flowing in, we can say net, is equal to the current flowing out, the net current flowing out. And so yeah, that's pretty much what it means. And this seems pretty intuitive. What goes in goes out. And so you may ask me, well, what is a junction? Well, a junction is really just where multiple elements meet. Where multiple elements meet. So take, for example, a wire with only one element. There is no junction on this particular drawing. However, if I took something that looked like this, we do have a junction. We have a junction right here because two elements are meeting right here in the center. And what they mean by element is the element's respective wire, because these elements change the currents flowing through these wires, or they can. But nevertheless, this is still a junction. Okay, so let's just look at this example for a little bit longer. This example right here. If we had these two, or if we did have, something like this inside our circuit, well, what's the point? Well, what's the point of all this? Well, all it's saying is that the current flowing in, so let's just draw some arrows. So let's imagine that this was the arrow going in this direction, and there's another current flowing that direction. These are just arbitrarily assigned. I could have easily made the arrows point at each other or point in opposite directions. Let's just say they're pointing this direction, and this was current 1, so the current flowing through here is current 1, and the current flowing this direction is current 2. All it's saying is that current going in, so I1, is equal to current going out, which is I2. And by this current definition, it also implies that I1 minus I2 is equal to 0. And so we can also add this to our definition, that this implies that current in net minus current in out is equal to 0. That's what it means. That's what Kirchhoff's current law means. And this is, of course, in reference to a junction. So let's take this other example, this orange one right here. If we imagine that we had currents that went like this, one was flowing in, this one's flowing out, and this one's flowing out. And you give these elements with currents flowing through them names. So the current flowing through this one is I3, the current flowing through here is I2, the current flowing through here is I1. And we have a junction, which is where these three elements, I'm going to name them 1, 2, and 3, meet up. And that's also another thing. Don't be worried about these boxes. They're just another way of symbolizing resistors, which also look like this. But for our purposes, that's not too important. So, what would be the equation for this? Well, it would be the currents flowing in, so I1, I3, or I1 is equal to the current flowing out. So I2 plus I3. Flowing out from this junction, of course. And so, well, you might want to ask me, well, what if this arrow was wrong? What if it was wrong? We want a different arrow. What if I said that I3 actually, I'm going to color this in green. What if I said it flowed in this direction. This direction. And I could have drawn the arrow like this. It doesn't really mean anything. It's the same thing. So let's say I drew like this. That means I1 is flowing in, I3 is flowing in, is going to be equal to I2. So the current of I1, the current I3, and the current I2 will be represented by this equation. But you may ask, you may start to wonder, well, isn't that going to change our I values? And the short answer is no, because current can be negative or positive. We can, for example, we can have, let's just say we had 2 amps. That 2 amps could be negative 2 amps. All this negative and positive, all it means is direction. So direction. So take, for example, take, for example, that I1 was equal to 5 amps and I2 was equal to 10 amps. Let's just say it's 10 amps. If this were the case, based on our equation, based on if we were using this green arrow, we would get that I3 is equal to 5 amps. So, because I1 is 5 amps, plus I3 is equal to 10 amps, I3 is going to be equal to 5 amps. And all this means, because it's positive, is that the current is truly flowing in this direction. If we were to use this, if we were to return to this purple arrow from earlier, so let me erase this. So if we were to return to this arrow, oh, that's not good. If we were to return to this arrow, I'm just going to cross this out, cross this out. Let's just say our arrow was back again, moving in this direction. You know, you're saying this direction. You may guess what might happen. Well, we would base it off of I1 equals I2 plus I3. But I1 is still 5 amps, and I2 is still 10 amps. What's going to happen? Just take a moment and think about it. Well, I'm going to assume that you've had some time to think about it, and the short answer is we would get the same value. What would happen is we would say I1 is equal to 5 amps. This is much too small. It's going to be equal to 5. It's going to be I1 is going to be equal to 5 amps. So we're going to, oh, well, let me write this over here. 5 amps is going to be equal to I3 plus 10 amps. And so what we get is I3 is equal to negative 5 amps. And all this means is the true current is still flowing in this direction, which is the same as this blue arrow that we got from this equation right here. And so true direction never really changes. The negative really just means that current is actually flowing in the opposite direction. So I can say over here, negative current means that current is flowing opposite to our arrow. Magnitude should not change if we've solved properly. Magnitude of I shouldn't change. And that's pretty much what it means. So let's take this last example. let's say we're gonna assign our elements. Let's say this is element 1, this is element 2, this is element 3, and this is element 4. Let's label some currents, I1, let's say it's I2, let's say this is I3, let's say this is I4. And then let's give it some currents, so let's say, or a current direction. So let's say this flowed that way, that flowed that way. But wait, I can assign arrows arbitrarily. So if I just assigned it this way, oh, we get something interesting. The currents flowing into this junction add up to something to nothing. And what I mean by that is there's no outflow. So that means I1 plus I2 plus I3 plus I4 flow into the red junction, and they all add up to nothing, so 0. And based on the previous example, what this means is if we actually solved for all of these currents, what we would find is at least one current is going to be negative, or most likely going to be negative, if based on this arrangement. It's highly unlikely that we're just going to have 4 currents flow in and they're all positive and they're going to meet up right here and just clash and equal 0. It's just we haven't learned of a situation that would happen. So the reality is one of these currents, at minimum of one of these currents, is probably going to be negative. So take, for example, let's just say I1 is equal to 5 amps. And let's say I2 is equal to 5 amps. Let's say I3 is also equal to 5 amps. What is I4 going to be equal to? Well, I4, based on this equation right here, is going to be equal to negative 15 amps. And what that means is the true direction of this current is going to be flowing opposite to what the arrow we've assigned, and the magnitude of this current will be 15 amps. And so the flowing in, we would call it negative 15. This would be 5 amps, this would be 5 amps, this would be 5 amps, and the true direction would be denoted right here. So this fits what we said over here, and that's pretty much Kirchhoff's current law.